On October 2nd, 2025, the most powerful camera ever sent to another planet pointed its lens not at Mars below but upward at a strange visitor racing through our solar system. The high-rise camera aboard the Mars Reconnaissance Orbiter orbiting high above the red planet captured the sharpest images yet of something nobody had ever seen before, an object from beyond our solar system called Comet 3I Atlas. These images, taken from incredibly far away, would show something about that comet that had scientists around the world scratching their heads and asking questions they had never asked before. What exactly was this visitor? Where did it come from? And why was it behaving in ways that seemed to challenge everything we thought we knew about comets? Here's the thing about visitors from outer space, and when I say outer space, I mean the truly far away kind, from another star system entirely. They are almost impossibly rare to study up close. Before this year, scientists had discovered only two objects that came from outside our solar system. The first one, called Oumuamua, zoomed past us so quickly in 2017 that we barely got a good look at it. The second one, called 2I Borisov, appeared a couple of years later and gave us a bit more time to observe it. But here's where things get interesting. The comet we are about to explore together, 3I Atlas, is the third interstellar object ever confirmed, and it is doing something very unusual right now. It is the closest we have ever gotten to studying one of these cosmic wanderers in such incredible detail. And according to Avi Loeb, a Harvard scientist who has been carefully watching this object through telescopes and through the research of other scientists all around the world, something about 3I Atlas is raising some very big questions indeed. Let me back up for just a moment and help you understand what makes a comet special in the first place. If you have ever watched a meteor shower or seen what people call a shooting star, you have actually seen a piece of a comet burning up as it falls through Earth's sky. A comet is basically a giant ball of ice and rock and dust sailing through space. Most of the time, comets hang out in the far reaches of our solar system, in a place called the Oort cloud, which is so far away that light from the sun takes hours to reach it. But sometimes something nudges a comet, maybe the gravity of a passing star or a collision with another space rock, and it starts falling toward the sun. As it gets closer and closer to the warmth of the sun, that icy ball starts to heat up. The ice on its surface begins to melt and bubble and escape into space as vapor. This creates what we call a coma, which is like a giant halo of gas and dust surrounding the comet's solid center. Sometimes this vapor gets blown back by the solar wind, the stream of particles flowing out from the sun, creating that beautiful tail we see in pictures of comets. The tail always points away from the sun like hair being blown by an invisible wind. But here is where 3I Atlas becomes truly interesting. When it was first discovered, way back on July 1st, 2025, by an automated telescope in Chile, it looked like any other comet might look. But as it got closer and closer to the sun throughout the summer and early autumn, something very strange started happening. The observations that scientists were making through their telescopes showed something that had never been quite seen before. For the first time in recorded history, scientists were watching an interstellar comet get close enough to the sun to become truly active, to really start releasing gas and dust into space, and doing so in ways that seemed unusual compared to the comets we have studied that came from within our own solar system. By September 2025, about 3 months after its discovery, the comet had transformed in a way that caught everyone's attention. In the early months, observations through telescopes showed something called an anti-tail, which is a tail that points toward the sun rather than away from it. This anti-tail appeared like a jet of material shooting directly at the sun. It was narrow and intense and bright. But then, as the comet got even closer to the sun, something remarkable happened. That anti-tail gradually transformed into a regular tail, pointing away from the sun, the way most comets behave. Scientists at the Nordic Optical Telescope in the Canary Islands in Spain, along with researchers using other telescopes around the world, documented this change through their observations. It was as if the comet were changing its behavior, adapting to its environment as it approached the sun. This is where Avi Loeb comes into the story in a meaningful way. Loeb is not just any scientist. He is the director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, which means he works at one of the most respected places for studying the universe in the entire world. Before that, he was the chair of the astronomy department at Harvard University. He has thought deeply about big questions regarding what might exist in our universe beyond what we have already discovered. Some of his ideas have been controversial. Some of his colleagues agree with him strongly. Some do not. But what cannot be disputed is that he thinks carefully and deeply about the universe and looks at evidence very seriously. When 3I Atlas was first discovered, Loeb, along with colleagues from the Initiative for Interstellar Studies, published a paper raising a question that grabbed headlines and caught people's imaginations. They asked whether this object might be something other than a natural comet. They pointed to several things that seemed unusual. The object appeared to be larger than you would expect for an interstellar comet. Its trajectory, or path through space, seemed remarkably aligned with the plane of our solar system, which some found improbable. The object had features that were hard to explain using the standard ideas about how comets behave, and so they asked the question that nobody was supposed to ask out loud. Could this be an artificial object? Could this be a spacecraft? Now, it is incredibly important that I stop here and be very clear about something. The vast majority of astronomers and scientists who study this object believe that 3I Atlas is exactly what it appears to be, a natural comet from another star system, behaving in ways that comets should behave. The American Space Agency NASA has published statements saying they have no evidence of anything artificial about this object. The European Space Agency and the Japanese Space Agency have all been studying this comet intensively, and all the mainstream scientific evidence points to a natural origin. When we say we need to keep an open mind and look at the evidence carefully, what we are really saying is that we should never assume something is impossible just because it seems unlikely. That is the scientific method at work. We look at the evidence, we form ideas, we test those ideas, and we follow where the evidence actually leads. But here is what makes this story so captivating right now, in October of 2025. The very latest observations are actually supporting the natural comet explanation, and these observations are fascinating for their own reasons, quite apart from any speculation about alien spacecraft. In the months leading up to October, scientists were carefully watching how the comet was behaving as it approached the Sun. The James Webb Space Telescope, one of the most powerful instruments humans have ever built, turned its infrared spectrograph toward the comet in early August. This instrument does something pretty amazing. It breaks apart the light coming from the comet into its component colors, like a prism makes a rainbow from sunlight. By studying which colors are brightest and which are faintest, scientists can figure out what chemicals are present in that light. When the Webb telescope looked at 3I Atlas, it detected the unmistakable signatures of several different chemicals. Carbon dioxide was there in abundance. Water ice was present. Carbon monoxide was detected. Carbonyl sulfide, which is a compound containing carbon, oxygen, and sulfur, was also found. And so the first real evidence about what this comet is made of came into focus. It appeared to be an icy body rich in gases that would sublime or turn from solid to vapor as it heated up. Here is what sublime means in this context. When you take dry ice from a freezer and leave it on a table at room temperature, you might notice that it seems to disappear into thin air. It does not melt into a puddle like regular ice does. Instead, it transforms directly from a solid into a gas, skipping the liquid stage entirely. The dry ice sublimates. On 3I Atlas, as the comet approached the Sun, the intense heat was causing these frozen gases, particularly carbon dioxide and water, to sublime. They turned from solid to vapor and escaped into space. This process released enormous amounts of energy and created pressure that pushed dust and other materials away from the comet's surface, creating that bright halo and that tail. By August, according to measurements made by observatories around the world, the comet was losing mass at an absolutely astonishing rate. Scientists calculated that approximately 150 kilograms of material were escaping from the comet every single second. If you tried to visualize that, imagine taking the weight of a small car, roughly 1,500 kilograms, and losing that much mass every 10 seconds. That is how intensely the comet was outgassing, and this rate was only increasing as the comet continued its approach toward the Sun. Now let's talk about what happened as we moved deeper into September and then into October. The observations that Jewett and Lu, two very accomplished astronomers, made with the Nordic Optical Telescope showed something remarkable. The anti-tail, that jet of material pointing toward the sun, had indeed transformed. The theory that Avi Loeb had developed, working with another scientist named Eric Kito, explained why this was happening. As the comet got closer to the sun, the temperature dependence of sublimation became increasingly dramatic. Basically, the warmer the comet got, the faster the frozen gases escaped. This caused a sharp increase in the production rate of ice fragments, the little particles of water ice being ejected from the comet's surface. But it also meant these particles did not survive as long in the stream of outflowing material. The combination of more particles being produced but fewer particles surviving for long periods created a shift in where the maximum brightness of the material could be observed. The simple ice particles gave way to larger, longer-lived particles made of refractory dust, that is, dust that does not melt or sublimate easily at high temperatures. These larger particles could travel farther from the comet before they faded away, which is why the tail pattern changed. And then something happened that made the entire scientific community hold its breath with anticipation. On October 3, 2025, the comet made its closest approach to the planet Mars. It passed within 30 million kilometers of the red planet. ESA's Mars orbiters, the Mars Express spacecraft and the ExoMars Trace Gas Orbiter, both turned their cameras towards the comet. One of these spacecraft had been orbiting Mars since 2016, studying the planet in exquisite detail. These cameras are built to photograph the surface of Mars from just a few hundred to a few thousand kilometers above the ground. Using them to photograph a comet 30 million kilometers away was like using a wide-angle lens to see something incredibly distant. But these spacecraft managed to capture images of the comet, showing its glow and its tail against the backdrop of space. The images came back and revealed the diffuse coma, the glowing halo surrounding the comet. They showed the tail structure, and they provided more evidence that 3I Atlas was behaving exactly like a natural comet behaves. But the images that everyone was really waiting for came from another source. NASA's Mars Reconnaissance Orbiter carries a camera called HiRISE, which stands for High Resolution Imaging Science Experiment. This camera is one of the most powerful remote sensing instruments ever placed in space. It has taken stunning pictures of the Martian surface that show details smaller than a house from hundreds of kilometers up in orbit. When 3I Atlas passed near Mars, this camera was pointed not at Mars but at the comet itself. The images were captured on October 2nd, 2025, just before the comet's closest approach. But here is where the story hit a frustrating snag. The images were captured, they were taken, they were preserved in the spacecraft's memory. But at the time these images were supposed to be released to the public, the United States government went through what is called a shutdown. Government agencies stopped operating. The release of these images was delayed. Scientists and the public had to wait to see what the most detailed pictures yet of an interstellar comet would show. At the exact moment in time that we are telling this story, in late October 2025, these images have not yet been released to the world. They remain hidden away in the Mars Reconnaissance Orbiter, waiting for government operations to resume. This has frustrated scientists like Avi Loeb, who has expressed, perhaps a bit harshly, that the government could release the scientific data even if administrative offices were closed. The scientists are eager to see what HiRISE revealed. These images, when they are finally released, will show the comet from a sideway angle, which will give a much clearer three-dimensional view of the cloud of material surrounding the comet than we can get from Earth. At a pixel resolution of 30 kilometers, even distant images will show features that Earth-based telescopes simply cannot see. These will be crucial to testing the models that Loeb and Kito have developed to explain the transition from anti-tail to regular tail. But the story does not stop in October. The comet was scheduled to reach its absolute closest point to the Sun on October 29, 2025. At this point, called perihelion, the comet would be only about 1.4 astronomical units from the Sun. An astronomical unit, which we call an AU, is the distance from Earth to the Sun, so the comet at its closest would be 1.4 times farther from the Sun than Earth is. This sounds far, but remember that Mars orbits at about 1.5 AU, so the comet was passing inside Mars's orbit. At this point, the comet would experience an incredible amount of solar radiation, more than 33 gigawatts of power, according to Loeb's calculations. To put this in perspective, this is equal to the power generated by 33 large nuclear power plants, all focusing their energy on a single ice ball 5 kilometers across. The comet would be experiencing intense heating, and the rate of outgassing would reach its maximum. After passing its closest point to the Sun, the comet would begin traveling back out into space. On December 19, 2025, it would reach its closest approach to Earth, though it would still be about 1.8 times the Earth-Sun distance away, far enough that there was no possibility of any collision or dangerous close encounter. But by that point, the comet would be moving away from the Sun, cooling down, and its activity would gradually decrease. The tail would begin to fade, the brightness would diminish, and eventually, over the course of months and years, the comet would become too faint to observe and would disappear back into the interstellar darkness from which it came. This brings us to an important question that Avi Loeb and others have raised, even as they acknowledge that the comet appears to be natural. Loeb, in his analysis, has been looking beyond just the scientific features to consider implications. He points out that if a spacecraft were ever sent from another star system to observe Earth, the most efficient way to do this would be to approach close enough to the Sun to gain speed through what is called an Oberth effect. This is a concept from physics and astronautics. When a spacecraft is moving very fast, which happens when it is closest to a massive object like the Sun, a small burst of engine power produces a much bigger change in the spacecraft's velocity than it would at slower speeds. So if you wanted to speed up or slow down a spacecraft efficiently, you would do it at closest approach to the Sun. It would be the most energy-efficient way to do it. Now, here is where Loeb is asking a very specific question. 3I Atlas is scheduled to pass behind the Sun from Earth's perspective on October 21, 2025. This means for several weeks we cannot see the comet from Earth at all because the Sun is in the way. Loeb asks, could this be an ideal time for some kind of maneuver? Could this be when a hypothetical spacecraft might make some kind of adjustment to its trajectory? And would we even be able to detect it if it did? He explicitly states that he thinks the object is most likely a natural comet, but he argues that the remote possibility of an artificial origin, while small, should be considered seriously because of what it would mean for humanity. It would mean we are not alone. It would mean someone else has figured out how to travel between the stars. It would mean we have been visited. But, and this is crucial, he is also clear that he is willing to change his mind if the evidence changes. He has proposed what he calls the Loeb scale, a way of ranking how likely an object is to be artificial based on its characteristics. As more evidence comes in showing that 3I Atlas behaves like a natural comet, his ranking on this scale should go down. He has said that if, after passing its closest point to the Sun and experiencing intense solar heating, the comet shows all the features of a natural comet, he would reduce its rank on the Loeb scale to 2. It would not go down to 0 or absolutely natural because of certain features that remain unusual, like the enormous mass of the comet compared to previously known interstellar objects and its remarkably precise alignment with the plane of our solar system. But he would acknowledge that the natural comet hypothesis has been strongly supported. This is actually how good science works, even when it deals with extraordinary claims. You propose a hypothesis, you identify what evidence would support it or contradict it, you make predictions, and then you look at the actual evidence that comes in. If the evidence supports the hypothesis, it gains credibility. If the evidence contradicts it, the hypothesis must be modified or abandoned, and you remain willing to follow the evidence wherever it leads. So let's turn now to the broader picture of what we actually know about 3I Atlas based on all the observations that have come in so far. The composition is becoming clearer. That James Webb observation of the comet's spectroscopy revealed that the material escaping from the comet consists primarily of carbon dioxide, with smaller amounts of carbon monoxide and water. The percentages are roughly 87% carbon dioxide, 9% carbon monoxide, and 4% water by mass. This composition is actually quite interesting because it is somewhat different from typical comets that originate in our own solar system. The Oort cloud comets that visit the inner solar system tend to have different ratios of these materials. Some scientists have speculated that this difference in composition is evidence of the comet's truly foreign origin, that it formed in a different stellar system, probably orbiting a different star, and that it escaped its original system billions of years ago. The size of the comet has been estimated through careful observations. The Hubble Space Telescope observed the comet on July 21, 2025, and captured detailed images of the comet's nucleus, the solid center. Based on these observations, scientists have estimated that the nucleus has a diameter of somewhere between roughly 1.4 kilometers and 5.6 kilometers, with current estimates leaning toward the upper end of that range, around 5 kilometers. This makes 3I Atlas substantially larger than either of the two previously known interstellar objects. Oumuamua was estimated to be somewhere between 100 meters and a kilometer in length. 2I Borisov was estimated at around 1 to 4 kilometers in diameter, so 3I Atlas is bigger than at least the first and probably similar in size or larger than the second. The mass of the comet has been estimated through a clever application of physics. When an object travels through space, it experiences the gravitational pull of other objects. If the comet were shedding material through outgassing, and if we could detect the precise way this outgassing affects the comet's trajectory, we could estimate how massive the comet is. If the outgassing were affecting the orbit in a big way, that would suggest a lighter comet. If the outgassing had very little effect on the trajectory, that would suggest a heavier comet. Observations made by Avi Loeb and colleagues Richard Cloete and Peter Veers indicated that the outgassing was having a very small effect on the comet's trajectory. This suggested that the comet was quite massive. Their calculations concluded that the comet has a mass of greater than 33 billion tons. This enormous mass means that the material lost during its approach to the Sun, even though it amounts to millions of tons, is actually a very small fraction of the comet's total mass. Specifically, the calculations showed that from July through October 2025, the comet lost about 2 million tons of material. 2 million tons sounds like a lot, and in human terms, it is an absolutely staggering amount of mass. But when compared to a comet that weighs 33 billion tons, this loss amounts to less than 0.00005% of the comet's total mass. To give you another way of thinking about it, this is roughly equivalent to the ratio between the size of your palm and the size of the entire island of Manhattan. The comet shed a surface layer but barely scratched the surface. We cannot learn the true nature of the comet from the thin skin it has lost so far. We would need to see deeper into the comet itself to really understand what it is made of and where it came from. The speed of the comet is extraordinary. It entered our solar system traveling at about 58 kilometers per second relative to the Sun. This is its hyperbolic excess velocity, or as scientists sometimes call it, V infinity. This speed is much higher than the two previously known interstellar objects. Oumuamua was moving at about 26 kilometers per second. 2I Borisov was traveling at about 32 kilometers per second. 3I Atlas is moving faster than both of them. This faster speed tells us something important about how far away and how long ago the comet left its star system. Very fast interstellar objects have probably been traveling through space for much longer and have come from much farther away than slower objects. The trajectory of the comet follows what is called a hyperbolic path. This is different from the circular or elliptical paths that planets follow around the Sun. A circular orbit means an object goes around and around the same place forever. An elliptical orbit is stretched out, like an oval, but still closed. A hyperbolic orbit, by contrast, is open-ended. The object comes in from infinity, approaches the massive object causing the gravitational pull, passes closest, and then leaves, heading back out to infinity. It does not stay bound to the Sun. It will eventually escape our solar system entirely. The eccentricity of the orbit, a number that describes how stretched out or open-ended the orbit is about 6.14 for 3I Atlas. For comparison, the eccentricity of Earth's nearly circular orbit is about 0.016, so 3I Atlas is on a vastly more extreme trajectory. This extreme trajectory is one of the things that makes the alignment with the plane of our solar system, which Avi Loeb mentions as unusual, more striking. The probability of a random object from interstellar space passing through our solar system on a trajectory so neatly aligned with the orbital plane where all our planets go rather than coming in at some wild angle is quite small. Let me help you understand why this matters. Imagine you are standing in a big field and you throw a ball toward a target that is far away. If you throw it randomly, most of the time it will not travel along a particular line. It will come in at whatever angle your throw happened to send it. But what if you threw the ball 100 times and found that most of them came in along a very specific direction, all aligned with a particular line on the ground? That would be surprising. You would wonder if something was directing the throws. That is the kind of surprise that the alignment of Three-Eye Atlas with the ecliptic plane represents. It is not impossible. It is not even impossible enough to say it could not happen by chance, but it is more unlikely than a random trajectory would be. This is one of the reasons Loeb thinks it is worth keeping an open mind about the object's origin, even as the majority of the evidence points to it being a natural comet. Now let's think about what we can actually expect to learn as time goes on. The observations in late October and November of 2025 will be absolutely crucial. After the comet passes behind the Sun from Earth's perspective around October 21st, we will not be able to observe it from Earth for a while. But space-based missions will have a different perspective. ESA's JUICE mission, the Jupiter Icy Moons Explorer, will have an opportunity to observe the comet in November 2025. Although JUICE is much farther from the comet than the Mars orbiters were, it will be observing the comet just after it reaches perihelion, when the comet will be at its most active. The spectrometers and cameras aboard JUICE will be able to gather data on the comet at its peak activity, and another spacecraft, the Europa Clipper, may actually pass through the ion tail of Three-Eye Atlas during the period from October 30th to November 6th. The ion tail is the tail made of charged particles, different from the dust tail. When a spacecraft passes through a comet's tail, it can make measurements of the plasma, the hot ionized gas, and the magnetic fields embedded in it. These measurements would provide entirely new information about how the comet's tail behaves as it passes through the solar wind. By early December, the comet will emerge into the morning sky again, visible from Earth once more. It will be growing dimmer as it pulls away from the Sun, but the period from December through early 2026 will still offer opportunities for detailed observations. The comet will reach its closest approach to Earth on December 19th. Although this will still be about 1.8 AU away, nearly twice the Earth-Sun distance, it will be closer than it ever gets again. This will be the time when Earth-based telescopes can achieve their highest resolution observations of the comet. This will be when the most detailed pictures from the ground can be taken. After December, the comet will continue to fade. It will move through the constellations of the sky, traveling through Virgo and Leo. Its brightness will drop below what can be seen even with modest amateur telescopes by late December. By January and beyond, it will require increasingly powerful equipment to observe. Within a year or so, the comet will become too faint to observe at all. It will fade to invisibility, and eventually, after weeks and months and years of travel through space, Three-Eye Atlas will escape our solar system entirely. It will return to the interstellar void from which it came. The few observations we have made during this brief encounter, just a handful of months when the comet passed through our neighborhood, will be all we ever know about this particular visitor from the stars. This is what makes this moment, right now, in October and November 2025, so incredibly important scientifically. This is the window. This is the opportunity. After this, there will be no more Three-Eye Atlas observations. It will be gone. The next interstellar object might not arrive for years or decades, and that next object might behave differently. It might teach us different lessons. So everything we learn from Three-Eye Atlas right now is precious. Every observation counts. Every spectrum taken, every image captured, every measurement made, all of it adds to our knowledge of what interstellar objects are like, where they come from, and how they behave when they encounter our Sun. Now, Avi Loeb's comments about Three-Eye Atlas have been widely reported and have captured public imagination partly because he is willing to ask the question about whether this could be artificial. But what exactly has he been saying, and what is the evidence he is basing this on? Let's break this down more carefully. Back in July, when the object was first discovered and before all these detailed observations came in, Loeb and colleagues published research suggesting that the object had several unusual characteristics. First, there was the apparent large size. Most interstellar objects we discover are quite small, mere kilometers across or even less. But 3I Atlas appeared to be 5 kilometers across, making it several times larger than we would statistically expect. Second, there was the lack of identifiable chemicals in the early observations. At first, it was hard to tell what the comet was made of. For a natural comet, you would expect to see certain chemicals pretty quickly. Third, there was the trajectory question. The alignment with the ecliptic plane is, as we have discussed, improbable by random chance. From these observations, Loeb and his colleagues asked whether we should consider the hypothesis of an artificial origin seriously. But it is crucial to understand that even Loeb does not claim this is the most likely explanation. He places it as a remote possibility, a what-if worth considering given the evidence. He developed his scale to quantify how much evidence an object would need to show to make an artificial origin more probable than a natural origin. An object at level 0 on the Loeb scale would be definitively natural. An object at level 10 would be probably artificial. 3I Atlas, based on the early observations, was rated at around level 3, still most likely natural, but with a few features worth noting. But here is what has happened as more observations have come in. The spectroscopic data from the James Webb Space Telescope clearly identified carbon dioxide, water, carbon monoxide, and other chemicals, exactly what you would expect from a natural comet. The behavior of the object as it approached the Sun has matched the theoretical predictions for how a natural comet should behave. The structure of the anti-tail and its transition to a regular tail have been explained by perfectly ordinary physics: sublimation, heat transfer, particle scattering. All of this evidence points toward a natural comet. And as all this evidence has accumulated, the apparent anomalies that seemed so striking in July have become less surprising. The large size, while unusual, is not unprecedented. The chemical composition, now that we have identified it, is consistent with a cometary object. The trajectory, while improbable, is not impossible. It just means we got lucky with our viewing angle and location. So what is Loeb saying now, as of October 2025, in light of all this new evidence? He is saying that the object appears most likely to be a natural comet, but he is also saying that we should wait for the final evidence. He is saying that if the comet, after experiencing intense solar heating at perihelion, shows all the characteristics of a natural comet, then its rank should drop. If everything looks natural, then it probably is natural, but he also notes that even if it is natural, some of the unusual characteristics will not completely go away. The enormous mass compared to previously known interstellar objects will still be an unusual feature. The alignment with the ecliptic plane will still be improbable, even if explained by statistical chance. So there will always be something a little unusual about 3I Atlas, even if its origin is definitely natural. This is actually a very reasonable scientific position. It is not the sensational, "I think this might be an alien spacecraft" that you might read in some headlines. It is more nuanced than that. It is, "I think this is probably a natural comet, but I will keep an open mind about unusual possibilities, and I will change my conclusions if the evidence warrants it." This is how good science actually operates. The headlines make it sound more dramatic than the actual scientific position, which is how headlines tend to work. But there is something more to understand here, and it goes beyond just 3I Atlas. There is a broader question about why someone like Avi Loeb would even raise these ideas in the first place. What is he really trying to do? The answer involves understanding his broader work. Loeb is the head of the Galileo Project, an initiative focused on studying the evidence for technology beyond Earth. The name itself is a reference to Galileo Galilei, the scientist who pointed a telescope at the sky in the 1600s and made observations that fundamentally changed how we understand the universe. Loeb has argued that just as Galileo transformed our understanding by actually looking at the evidence rather than relying on assumptions, we should be willing to actually look for evidence of technology beyond Earth rather than assuming we would never find it. This is not a fringe position in the way it is sometimes portrayed. Loeb has credentials as a serious scientist. He has published hundreds of peer-reviewed research papers. He has taught at Harvard University. Many of his colleagues respect his work, even when they disagree with some of his conclusions about extraterrestrial technology. The Galileo project has become more mainstream, with genuine research programs studying a range of phenomena. The key insight that Loeb and others in his field are trying to convey is simply this: we should not be afraid to ask questions. We should not be afraid to collect evidence. We should not be afraid to consider possibilities that might seem unlikely. And if we do that, we need to do it carefully, scientifically, and with proper statistical rigor. We need to say what we are confident about and what we are uncertain about. Now, coming back to 3I Atlas itself, what would it mean if this object turned out to be artificial? What would that actually imply? For one thing, it would mean that someone else had figured out how to travel between the stars. This is an accomplishment we have not yet achieved. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at about 190 kilometers per second. That sounds fast, but it is still slower than 3I Atlas's speed. To travel between stars, you need to reach these kinds of speeds and maintain them for years or decades or centuries. That requires either extremely efficient propulsion systems or extremely patient civilizations willing to wait a very long time for their spacecraft to reach distant stars. If 3I Atlas were an artificial probe, it would also suggest that whoever sent it was advanced enough to want to study the inner solar system with such intensity. Why send a probe so close to the Sun? The answer might involve several possibilities. If you are trying to observe a solar system, the Sun is the central object. Getting close to the Sun allows you to study the system more carefully. It also allows you, if you have advanced technology, to use the Sun's gravity and radiation for various purposes. You could harness the Sun's energy. You could use its gravity to change your trajectory. There might be scientific reasons for getting close. There might be practical reasons. But whatever the reasons, the fact that 3I Atlas is approaching so close to the Sun suggests that if it were artificial, the civilization that sent it had very advanced capabilities. What would such a discovery mean for humanity? It would mean that we are not alone in the universe. It would mean that intelligent civilizations had existed before us, had developed space travel, and had ventured out to explore or study other star systems. It would be the most profound discovery in human history. It would force us to completely reconsider our place in the cosmos. We would no longer be the only known intelligent beings. We would be one among many. This would have implications for how we understand ourselves, for our philosophies and religions, for our future plans. It would inspire some people. It would frighten others. It would be, without question, the biggest news ever. But, and this is important, we also need to be very careful about certainty. At this moment, the evidence points overwhelmingly to 3I Atlas being a natural comet. The vast majority of scientists who have studied this object believe it is natural. The observations that have come in over the past several months have been consistent with natural comet behavior, unless the evidence changes dramatically, unless the December observations or the eventual data release from HiRISE shows something completely unexpected. The most honest scientific conclusion will be that 3I Atlas is a natural comet from another star system. That is still an incredibly exciting discovery. It is still a rare and precious opportunity to study an interstellar object in detail. It still teaches us important things about how comets form and behave in different stellar systems. It does not require an artificial origin to be fascinating and important. So what we are really witnessing in this moment of late October 2025 is a kind of crossroads in understanding. On one path, the evidence continues to accumulate showing natural behavior, and we eventually conclude that 3I Atlas is a natural comet. Still remarkable, still important, but fitting within our current understanding of the universe. On the other path, some unexpected observations emerge that challenge our understanding, and we are forced to consider new possibilities. Avi Loeb and his colleagues are essentially saying, let's stay open to both paths until the evidence decisively points to one or the other. And then, once the evidence is clear, let's follow it. That is what science should do. In the meantime, the observations continue. Scientists from multiple countries and multiple space agencies are working together to study 3I Atlas. The US Space Agency NASA has its facilities pointed at the comet. The European Space Agency is observing with its Mars orbiters and its Jupiter-bound spacecraft. The Japanese Space Agency has instruments dedicated to the study. Ground-based telescopes from universities and observatories around the world are collecting data. Amateur astronomers are contributing observations. This global effort reflects the recognition that this is a rare opportunity. This is a visitor from the stars that may not come again for decades. Every observation, every measurement, every spectrum adds to our understanding. So as we wrap up this part of the story and prepare to explore the related objects and concepts that have emerged from the study of 3I Atlas, let me offer a summary of where things stand. In July 2025, an automated telescope in Chile discovered an interstellar comet. At first, some scientists, including Avi Loeb, raised questions about whether it might be artificial, but as observations accumulated through August, September, and October, the evidence increasingly pointed to a natural origin. The comet's composition, as revealed by spectroscopy, consists of water, carbon dioxide, and carbon monoxide, exactly what you would expect from a natural comet. Its behavior as it approached the Sun matched theoretical predictions. The unusual anti-tail transformed to a regular tail through well-understood physics. The mass, while large for an interstellar object, is not incompatible with a natural comet, and so the probability of an artificial origin has decreased as more evidence has come in. But Loeb has also argued, with some scientific justification, that the improbable alignment with our solar system's orbital plane and the unusual size compared to previously known interstellar objects might warrant continued caution about complete certainty. The most honest position is that 3I Atlas appears to be a natural comet, but we should await all the evidence before claiming absolute certainty. To truly understand what makes 3I Atlas remarkable, we need to understand the context of interstellar object discovery. 3 objects, that is all we have ever found for certain that originated outside our solar system and passed through our cosmic neighborhood. For most of human history, we did not even know that such objects could exist. We thought that every comet, every asteroid, every bit of matter we saw in the night sky belonged to our solar system. The idea that something could come from beyond our solar system and pass through it was science fiction. But then, in September of 2017, everything changed. That is when 1I Oumuamua arrived. This name is Hawaiian, chosen to honor the place where it was discovered, Hawaii. Oumuamua means a messenger from afar arriving first in the Hawaiian language. And that is exactly what this object was. It was a messenger from afar. It arrived before any other interstellar object we had ever discovered. The observatory that discovered it was the Pan-STARRS 1 telescope, located in Hawaii. The name Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. Basically, it is a powerful telescope that automatically scans the sky looking for objects. When Pan-STARRS detected Oumuamua on October 19, 2017, astronomers immediately recognized that something unusual had been found. The first clue was the object's trajectory. When you calculate the orbit of an object around the Sun, you can determine whether that orbit is bound or unbound. A bound orbit, like Earth's orbit or the orbit of any comet in the Oort cloud, will loop back around to the same place over and over. An unbound orbit, one with enough velocity and the right angle of approach, will bring an object past the Sun and then continue away into space forever, never to return. When astronomers calculated the trajectory of Oumuamua, they discovered that it followed an unbound hyperbolic orbit. The object came from outside the solar system, passed by the Sun, and would continue outward, eventually escaping the solar system entirely. This was the first confirmed interstellar object. Oumuamua was not very large. Current estimates suggest it was somewhere between 100 meters and about a kilometer in length. It was moving at about 26 kilometers per second relative to the Sun. It passed very close to the Sun, within an astronomical unit, and then was gone. We had only a brief window to observe it, just a few weeks. But in that time, astronomers gathered valuable data about the object's brightness, its color, and its composition. Interestingly, Oumuamua appeared to be a reddish color, suggesting that its surface had been altered by radiation over the billions of years it had been traveling through space. One of the most striking things about Oumuamua was its shape. Most comets and asteroids are roughly spherical or slightly elongated, but Oumuamua appeared to be extremely elongated, with a ratio of length to width of at least 10:1, and possibly as much as 10:1 or even more. It looked like a cosmic cigarette or a stick hurtling through space. This shape was unusual, though not impossible for a natural object. Asteroids can be extremely elongated, but the shape combined with the speed and the trajectory made Oumuamua fascinating to scientists. Was it a natural object or something more? Some researchers, including Avi Loeb, raised the question of whether it could be an artificial probe, but the mainstream scientific opinion quickly settled on a natural object. Probably a bit of material ejected from a distant star system wandering through space for billions of years. After Oumuamua passed through our solar system and disappeared into the outer darkness, scientists wondered if this was a one-time event. Would we ever see another interstellar object? The answer came in 2019, less than 2 years later. In August 2019, another object was discovered. This one was named 2I Borisov, named after the amateur astronomer who first detected it and following the naming convention for interstellar objects. Borisov was more clearly a comet than Oumuamua had been. It showed a coma and a tail, the unmistakable features of an active comet. It was estimated to be roughly 1 to 4 kilometers across, larger than Oumuamua. It was traveling at about 32 kilometers per second relative to the Sun. And it, too, was on a hyperbolic trajectory, confirming that it came from outside our solar system. The discovery of 2I Borisov was exciting because it suggested that interstellar objects were not incredibly rare freaks. The fact that we had discovered 2 in less than 2 years suggested that there might be many more out there. If you find 2 of something in a short period, there could be dozens or hundreds or even more that you just have not found yet. The discovery of Borisov also answered one question. Yes, interstellar objects can be comets with active outgassing. Borisov showed that these objects could release gas and dust just like solar system comets do. But Borisov also raised new questions. Its composition seemed different from Oumuamua. Its orbit was different. Its size was different. It was becoming clear that interstellar objects were not all the same. They had diversity. They came from different star systems. They had different histories. Each one might teach us something different about the cosmos beyond our solar system. For 6 years after the discovery of Borisov, no new interstellar objects were found. Scientists using the same detection methods that had found the previous 2 objects scanned the sky, but nothing new was detected. It seemed like maybe these objects really were quite rare. It seemed like finding 2 in the span of 2 years had been lucky. Then, in 2025, just as Borisov was fading from the scientific spotlight, a new object was discovered. 3I Atlas. This was the 3rd confirmed interstellar object, and right from the beginning it seemed different from the previous 2. First, there was the matter of detection. 3I Atlas was discovered by the Atlas system, an automated telescope in Chile specifically designed to search for asteroids or comets that might be a threat to Earth. This system is called the Asteroid Terrestrial Impact Last Alert System. On July 1st, 2025, the Atlas system in Chile detected an object that appeared to be moving with extreme velocity. Initial analysis suggested that the object was interstellar. Within hours, other telescopes were pointed at the object to confirm. Within days, pre-discovery observations were found in the archives of other telescopes, extending the known observations of the object back to mid-June 2025. And within weeks, the scientific community had confirmed this was definitely another interstellar object. But something was different about 3I Atlas compared to the previous 2 interstellar objects. It was much larger. Estimates based on Hubble observations put the diameter at somewhere around 5 kilometers, making it several times larger than either Oumuamua or Borisov. It appeared to be more massive based on the calculations of its gravitational effects, and it seemed to be moving faster through interstellar space before entering our solar system. 58 kilometers per second versus 26 for Oumuamua and 32 for Borisov. Its trajectory, while still hyperbolic and definitely interstellar, showed that improbable near alignment with the ecliptic plane that we discussed earlier. All of this made 3I Atlas stand out. It was not just another interstellar object. It was unusual, different, special. Why were these interstellar objects being discovered now? Why had they started appearing with increasing frequency? The truth is that we did not know for most of human history that these objects even existed. Our ability to detect them depends on having telescopes powerful and sensitive enough to spot distant, dim objects. It depends on having automated systems that can scan large areas of the sky and identify unusual objects. It depends on computational power to analyze the data and determine orbital trajectories. All of these capabilities are relatively recent developments. Humans have only been able to systematically search for faint objects with electronic detectors for a few decades. Automated surveys that can scan thousands of objects per night are even more recent, so it is not that interstellar objects suddenly started showing up. They have probably always been flowing through the galaxy, passing through star systems, visiting other solar systems. We are just now developing the ability to notice them. How many interstellar objects are out there? Scientists have tried to estimate this based on the rate at which we have been discovering them. If we have found 3 in 8 years, what does that suggest about the total population? Statistical models suggest that for every interstellar object the size of 3I Atlas that passes through our solar system, there might be many thousands of smaller objects. If that model is correct, at any given moment there might be thousands of interstellar objects hidden in the distant reaches of our solar system that we simply have not detected yet. They are too faint, too far away, or in parts of the sky we have not thoroughly searched. But out there, beyond the Oort cloud, passing by on their way to somewhere else, these silent wanderers persist. What does it mean that these objects are passing through our solar system? When you think about it, it is not that surprising. The Milky Way galaxy is a vast disk containing hundreds of billions of stars. Our solar system is one speck among all those stars, and the galaxy itself is just one galaxy among hundreds of billions of others in the observable universe. In this vastness, objects being ejected from star systems and wandering through the gaps between stars is exactly what you would expect. Every star system probably has its own population of objects, some bound to the star in orbits, some escaped and wandering. All of these escaping objects are traveling through interstellar space. Most of them will never encounter another star. They will drift through the galaxy forever, cold and dark. But statistically, some of them will eventually pass close enough to another star system to be detected by observers there. We are those observers. We are the ones who have spotted these wanderers. What can these interstellar objects teach us? Each one that we observe in detail tells us about the star system it came from. If we analyze the composition, the chemicals present, we learn what kinds of materials form in other star systems. If we observe the size and structure, we learn about the formation processes in those distant solar systems. If we study the trajectory, we can work backward and try to figure out which star it came from, or at least narrow down the possibilities. Some researchers have attempted to trace Oumuamua and Borisov back to their origins by calculating where they came from based on their current velocity and direction. Some calculations suggest that Oumuamua might have come from the nearby star Vega. Other calculations suggest different origins. It is hard to pinpoint exactly where these objects come from because the calculations require knowing their initial ejection speed and direction, which happened billions of years ago and is impossible to measure directly. But by studying multiple interstellar objects, we can build a better statistical picture of how these objects form and where they originate. The discovery of interstellar objects has also fundamentally changed how we think about life and civilization in the galaxy. If objects can travel from one star system to another, then, in principle, a spacecraft could do the same. A civilization with sufficiently advanced technology could send probes to observe other star systems. It could send generation ships with people aboard, traveling for centuries to reach a destination. It could do many things we currently can only imagine. So the very existence of interstellar objects serves as a proof of concept. It proves that the distances between stars, vast as they are not insurmountable. Material can travel these distances. If material can, then perhaps more complex objects can. Perhaps spacecraft can. Perhaps we will one day have the technology to do what these natural objects do. The interstellar objects teach us that the universe is connected. The gaps between stars are not absolute barriers. There is a possibility of flow, of movement, of connection across these vast distances. Now, with the discovery of 3I Atlas, we have a third data point. We have a third example of an interstellar visitor, and this one is different from the first two. It is larger, it is faster, it is more massive. its trajectory is more aligned with our orbital plane. So the question naturally arises, what does this diversity tell us? Some scientists argue that it tells us that interstellar objects are more varied than we initially thought. Others use the unusual characteristics of 3I Atlas to argue that we should keep our minds open about what these objects might be. But most would agree that we need more data. We need to study 3I Atlas carefully. We need to wait for the next interstellar object discovery. We need to continue monitoring these cosmic wanderers, learning what they have to teach us about the broader universe beyond our solar system. Understanding what 3I Atlas is made of requires understanding what comets are in general. Comets are some of the most primitive objects in the solar system. They are essentially frozen samples of the material from which the solar system formed, preserved in deep freeze for billions of years. Most of the comets we have studied come from the Oort cloud, a spherical shell of icy bodies surrounding our solar system at enormous distances. These comets have been sitting in the Oort cloud essentially unchanged for billions of years, maintaining their primordial composition. They have not been heated, altered, or modified the way the planets and the asteroids in the inner solar system have been. When a comet is disturbed and falls toward the Sun, it gradually heats up. As the temperature increases, the frozen materials on the comet's surface begin to sublimate. The process varies for different materials. Water ice begins to sublimate at relatively low temperatures, around 160 to 170 Kelvin, which is about -100 to -100 degrees Celsius. Carbon dioxide, or dry ice, sublimes at even lower temperatures, around 78 Kelvin. Carbon monoxide sublimes at around 81 Kelvin. These frozen gases, locked into solid form for billions of years, transform into vapor as they are warmed by solar radiation. As these gases escape from the comet, they carry small particles of dust and ice with them. The buildup of escaping gas and dust creates pressure on the comet's surface, almost like a very gentle explosion occurring everywhere on the sun-facing side of the comet simultaneously. This pressure pushes dust away from the comet and helps lift the gas into space. The result is the development of a coma, that fuzzy halo surrounding the comet, and eventually a tail. The tail forms because the solar wind, the continuous stream of charged particles flowing out from the sun, pushes the dust and gas away from the comet, stretching it out behind the comet like a wake behind a ship. Now, the composition of a comet is incredibly important to scientists because it tells us about the star system where the comet originated. The ratio of different volatile compounds, water, carbon dioxide, carbon monoxide, ammonia, and others, varies from comet to comet. Our solar system comets that we have studied typically show a certain pattern of ratios, but interstellar comets might show different ratios because they formed in a different star system, around a different star, under different conditions. By analyzing the spectrum of light coming from 3I Atlas, the James Webb Space Telescope revealed the signature of several different chemicals. But the breakdown was interesting. The chemical composition of 3I Atlas, as revealed by spectroscopy, consists approximately of 87% carbon dioxide, 9% carbon monoxide, and 4% water by mass. This is notably different from typical solar system comets. For example, most comets in our own solar system show a higher proportion of water relative to carbon dioxide. The fact that 3I Atlas is richer in carbon dioxide and carbon monoxide suggests that it formed in a system where conditions were different from ours. Perhaps around a different type of star, perhaps in a region of that star system where temperatures were lower or radiation was different. The exact reason for the composition difference is something scientists are still working out, but it clearly indicates an origin outside our solar system. What is interesting about carbon dioxide sublimation is that it creates unique phenomena that are not as pronounced with water ice. Carbon dioxide is sometimes called dry ice. When dry ice warms up, it sublimates directly from solid to gas without becoming a liquid. This process is very sensitive to temperature. A small increase in temperature can cause a huge increase in the sublimation rate. This is why, when 3I Atlas approached the Sun and experienced exponential increases in solar heating, the carbon dioxide outgassing rate increased so dramatically. The rate of sublimation is very sensitive to the temperature, and the temperature increased dramatically as the comet approached the Sun. This sensitivity to temperature is probably why we saw the anti-tail phenomenon. When the comet was at intermediate distances from the Sun, perhaps around 3 to 4 astronomical units, the solar heating was sufficient to cause rapid sublimation of carbon dioxide, creating a strong outflow of gas and dust. The small light particles of water ice that were ejected at this stage could not escape very far from the comet before the solar radiation pressure and the solar wind caught them and pushed them backward toward the Sun. This created the anti-tail, the jet pointing toward the Sun. But as the comet got closer and the solar heating increased further, the sublimation rate of carbon dioxide reached even higher levels. The ice particles being ejected were moving faster and were more numerous, but at the same time, the smaller ice particles which had dominated the earlier outflow began to evaporate completely. Larger, longer-lived dust particles took over. These larger particles had more survival time before evaporating. They could travel farther from the comet, and they were pushed away from the Sun, not toward it. This created the regular tail pointing away from the Sun, the conventional comet tail that we are familiar with. This transformation from anti-tail to regular tail, while perhaps seeming strange, is actually a natural consequence of the physics of sublimation and particle dynamics. It is not something that requires special explanation or exotic physics. It is something that theory predicts should happen, and 3I Atlas's behavior matched those theoretical predictions. This is why most scientists have interpreted this as evidence of natural comet behavior. But let's also think about what the composition tells us about the environment where 3I Atlas originated. The relatively high proportion of carbon dioxide suggests that the comet formed in a region where carbon dioxide was abundant. This could be in the outer regions of a star system where temperatures are so cold that carbon dioxide freezes into solid form. It could also suggest that the star system where 3I Atlas formed might have had different chemistry than our own solar system. Our solar system has relatively specific proportions of the elements that make up comets, based on what we call the solar abundance, the proportions of elements as measured in the Sun and in meteorites. Other star systems might have somewhat different proportions. Higher carbon abundance relative to oxygen, for example, could lead to higher proportions of carbon monoxide and carbon dioxide in comets. Some stars are relatively carbon-rich compared to others. The detection of water ice in 3I Atlas, while present in smaller amounts than carbon dioxide, confirms that water is present in this interstellar object, just as it is in solar system comets. Water seems to be a nearly universal constituent of icy bodies. Wherever you find comets in our galaxy, whether in our own solar system or coming from somewhere else, water is almost always present. This makes sense because oxygen and hydrogen are among the most abundant elements in the universe, and when they combine, they form water. So water should be common almost everywhere. The water in 3I Atlas, locked into ice, represents material that is billions of years old, material that formed before this comet was ejected from its original star system. When we talk about the discovery of interstellar objects, we must start with Oumuamua, the first confirmed object of its kind. On October 19, 2017, the Pan-STARRS 1 telescope in Hawaii detected something unusual moving through the solar system. The object was given the designation 1I Oumuamua, where the 1I indicates it was the first interstellar object confirmed, and Oumuamua is Hawaiian for a messenger from afar arriving first. The name is perfect because that is exactly what this object was, a messenger carrying information from a distant star system, arriving before any other confirmed interstellar object. When Oumuamua was first discovered, astronomers were surprised for several reasons. First, its trajectory was definitely hyperbolic, definitely interstellar. Second, it was moving quite fast relative to the Sun, about 26 kilometers per second relative to the Sun's motion. Third, it was quite far from the Sun when discovered, much farther out than Mercury, Venus, Earth, Mars, or the asteroid belt. The fact that something from outside the solar system had penetrated so far into the solar system and had not been discovered until it was already far inside the inner solar system suggested that there could be many more interstellar objects out there that we had simply not detected yet. The physical characteristics of Oumuamua were fascinating and somewhat puzzling. The object appeared to be extremely elongated, with a length-to-width ratio of at least 10:1, and possibly much higher. In other words, if you could see it up close, it would look like a stick or a cigar or a needle, not like a sphere the way most asteroids look. This extreme elongation was unusual, though not impossible for a natural object. Astronomy has taught us that objects can be shaped in many different ways. Asteroids can be elongated, comets can be irregular, moons can be weird shapes, but an object with such an extreme aspect ratio, such a high ratio of length to width, was striking. The color of Oumuamua was reddish. This reddish color is thought to be due to organic compounds on the surface that have been altered by billions of years of cosmic ray exposure. As Oumuamua drifted through interstellar space, high-energy particles called cosmic rays bombarded its surface. These cosmic rays broke apart organic molecules, creating reddish-colored residue. This process is similar to what happens to objects in our own solar system that have been exposed to cosmic rays for billions of years. So the reddish color, while striking, is actually quite understandable as the result of natural space weathering. Oumuamua's size was estimated based on its brightness and the amount of light it reflected. The estimates put it somewhere between 100 meters and a kilometer in length. This made it quite small, smaller than a typical mountain but larger than a tall building. Its mass would be enormous despite its relatively small size if it were made of solid rock, probably many millions of tons. But if it had a lower density, it could be lighter. Without being able to physically examine the object, scientists could only estimate based on indirect evidence. One of the most interesting questions about Oumuamua was whether it might be artificial, a spacecraft from another civilization. Avi Loeb and others raised this question. They pointed out that the extreme elongation and the unusual trajectory could be consistent with an artificial probe. They noted that a spacecraft designed to travel between stars might look different from a natural object. It might be shaped to be aerodynamic or streamlined, even though in the vacuum of space, aerodynamics do not matter. Or it might be shaped in some other way that reflects its engineered purpose. The idea of Oumuamua being an artificial probe captured public imagination. Books were written about it. News articles featured it. Scientists debated whether this could really be a spacecraft from another star system. But the mainstream scientific consensus on Oumuamua quickly settled on a natural explanation. Yes, the object is unusual. Yes, it has strange characteristics, but none of these characteristics are incompatible with a natural object formed through natural processes. Extremely elongated asteroids do exist. Objects with high albedo variations, spots of different brightness, do exist. Natural processes can create unusual shapes and colors. And so, while the mystery of Oumuamua remains in some ways, we do not fully understand all the details of its origin and nature. The most likely explanation is that it is a natural object, probably a fragment ejected from a distant star system wandering through the galaxy. One important aspect of Oumuamua is that it approached so close to the Sun and then left so quickly that we had only a very brief window to observe it. The object passed through the inner solar system in just a few weeks. Observations before the closest approach were possible, and observations after the closest approach were possible, but the overall window of observability was short. This meant we gathered only limited data about the object. We have an image or two showing the object, along with spectroscopic data and brightness measurements, but we do not have the kind of detailed multi-wavelength observations that we have for 3I Atlas or for 2I Borisov. The relative speed and the closeness of approach meant that Oumuamua passed through our solar system almost too quickly to really study. Where did Oumuamua come from? By calculating backward along its trajectory, scientists have attempted to determine its origin. Some calculations suggest it might have come from the nearby star Vega. Other calculations suggest different origins. The uncertainty arises because we do not know the object's initial velocity, how fast it was moving when it left its original star system. and we do not know exactly what direction it was moving. With these unknowns, calculating back to find the origin is difficult. It is like trying to trace a bullet back to its gun when you do not know how fast the bullet was fired or exactly what angle it was fired at. In principle, it is possible. In practice, the uncertainties are large. Now that we know Oumuamua exists, and now that we know other interstellar objects exist, scientists are looking back at historical data, trying to determine if Oumuamua was the first interstellar object to pass through our solar system, or if others came before and were just not detected. The reason we might have missed earlier interstellar objects is simple. We were not looking for them. We did not have the telescopes, we did not have the automated systems, we did not have the computational power to analyze data and identify unusual objects. Before the 21st century, astronomical surveys were much more limited in scope. A comet might have passed through the inner solar system 100 years ago or 1,000 years ago, and we would not have detected it unless it came very close to Earth and was bright enough to see in the night sky. Now that we have modern surveys running continuously, we are detecting fainter and more distant objects. So Oumuamua might be the first we have positively identified, but it was probably not the first to actually visit our solar system. What is the legacy of Oumuamua? It is this. It woke us up to the fact that the solar system is not a closed system. It is not isolated from the broader galaxy. Objects from the outside can pass through. More importantly, it made us realize that these objects are discoverable. We have the technology to detect them, we can learn about them, we can study them. Oumuamua opened a new window on the galaxy. Before Oumuamua, astronomers did not have systematic programs to search for interstellar objects. Now they do. Before Oumuamua, we did not know for certain that such objects existed. Now we do. And before Oumuamua, we did not know what questions we should ask about the broader galaxy. Now we know some of them. Oumuamua was literally a message from afar, as its name suggests. It was a message that we are not alone in the cosmos, even if we are still looking for the kind of otherness that would make us reconsider our place in the universe. After Oumuamua passed through the inner solar system and disappeared from view, scientists wondered whether that had been a one-time event. Would we ever see another interstellar object? The answer came less than 2 years later with the discovery of 2I Borisov. This comet was discovered in August 2019 by Gennady Borisov, an amateur astronomer in Crimea, who observed the object using his telescope. The discovery of 2I Borisov raised the possibility that interstellar objects were not exceptionally rare but might be a more regular occurrence. 2I Borisov was noticeably different from Oumuamua in several ways. First, it was definitely, unambiguously, a comet. It displayed a coma, a fuzzy halo of gas and dust surrounding the nucleus, and a tail, the characteristic features of an active comet. This proved that interstellar objects could be comets with ongoing outgassing and activity. Oumuamua had possibly been an inactive comet, or possibly a comet that had already lost most of its volatile materials. But Borisov was definitely active, definitely releasing gas and dust. Second, Borisov was closer to Earth at its closest approach than Oumuamua had been. This meant astronomers had a better view and more time to make observations. The comet passed through the solar system a bit more slowly, giving the astronomical community a longer observational window. This led to better data about Borisov than had been available for Oumuamua. Third, Borisov's composition was somewhat different from what was known about solar system comets. Spectroscopic analysis of Borisov revealed the presence of various compounds and ions, providing clues to the chemical makeup of this object from another star system. While not dramatically different from solar system comets, the proportions were different enough to suggest a different origin and formation environment. Fourth, Borisov was estimated to be larger than Oumuamua, where Oumuamua was probably 100 meters to 1 kilometer across. Borisov was estimated to be in the range of 1 to 4 kilometers in diameter. This made it a substantial object, a significant piece of material from another star system. The speed of Borisov was also different from Oumuamua, where Oumuamua had been travelling at about 26 kilometers per second relative to the Sun. Borisov was moving at about 32 kilometers per second. This faster speed suggested a different origin or a longer trajectory through interstellar space. faster objects have probably been traveling for longer and have come from farther away. One important aspect of the study of 2I Borisov was the attempt to trace it back to its origin. If you know the current velocity and direction of travel, and you know the position of various stars, you can work backward and try to determine where the object came from. Some calculations suggested that Borisov might have come from the star system of Kruger 60, a binary star system relatively close to Earth, about 13 light-years away. Other calculations suggested different origins. The uncertainty is similar to the uncertainty surrounding Oumuamua. Without knowing the exact initial velocity, we cannot pinpoint the origin with precision, but the exercise of trying to trace these objects back to their origins is valuable because it teaches us about how interstellar objects might move through the galaxy. The discovery of 2I Borisov, coming so soon after Oumuamua, suggested that interstellar objects might be more common than initially thought. If you find 2 rare objects within 2 years, what does that tell you about how many exist? Statistical models suggested that there might be many interstellar objects passing through the solar system all the time, but most are too faint or too far away for us to detect. Only the larger ones, or the ones that pass relatively close to Earth, are discovered. By the time 2I Borisov was discovered, scientists had already begun proposing new survey programs designed to find more interstellar objects. It was becoming clear that this new class of cosmic visitors was worth studying seriously. Like Oumuamua, 2I Borisov was also subjected to speculation about whether it might be artificial. Again, Avi Loeb and others raised the question, but again, the mainstream scientific community concluded that the most likely explanation was a natural object. Borisov showed clear evidence of cometary behavior, outgassing, dust production, a tail. These are the characteristics of natural comets. While the object is unusual, nothing about it is incompatible with a natural origin. After passing through the inner solar system and approaching its closest point to the Sun, 2I Borisov began moving away from the Sun. Its brightness decreased as it traveled into the outer solar system and eventually back out into interstellar space. By 2020, it had become too faint to observe easily. By the mid-2020s, it was essentially gone from view, off on its journey through the galaxy, carrying its information about the star system it came from back into the cosmic void. The significance of 2I Borisov lies partly in what it taught us and partly in what it represented. It taught us that interstellar comets were active, that they displayed behavior consistent with solar system comets, that their composition could vary. It represented confirmation that Oumuamua was not a one-time freak event, but evidence of a broader population of interstellar objects. And it raised the question, how many more are out there waiting to be discovered? When we talk about 3I Atlas, we are really talking about a piece of another star system. We are talking about material that formed around another star and has been wandering through space for billions of years. This concept connects to a broader field of study called exocometry science, the study of comets around other stars and comets from other star systems. For many decades, astronomers have known that other stars have planetary systems around them. The first exoplanet, a planet orbiting a star other than our Sun, was confirmed in 1995. Since then, thousands of exoplanets have been discovered, but stars with planets almost certainly also have comets. In our own solar system, we have the Oort cloud surrounding our Sun with billions or trillions of icy bodies. Other stars should have their own analogous structures. They should have comets floating in the cold regions around them. Some stars are known to have debris disks, structures of dust and material orbiting the star. These debris disks are thought to be similar to the asteroid belt or the Kuiper belt in our own solar system. Some of them are thought to contain comets. When one of these distant stars is observed carefully, especially using the Spitzer Space Telescope or other infrared instruments, the heat signature of these debris disks can sometimes be detected. The presence of infrared radiation tells us that dust is being produced. The dust is probably being produced by collisions between larger bodies or by the sublimation of comets. So while we cannot always see the individual comets around distant stars, we can sometimes see evidence that they exist. But what is really remarkable is when one of these distant comets actually escapes its star system and passes through our solar system. That is a direct sample. That is physical material we can actually study from another star system. That is what Oumuamua and Borisov and 3I Atlas represent. They are not just evidence that other star systems have comets. They are actual samples of cometary material from those systems. They are celestial ambassadors carrying information about their home systems. The study of interstellar objects fits into a broader context of astrobiology and the search for life beyond Earth. While comets themselves are not living, at least not in any form we have found so far, they are repositories of information about the materials that might be available in other star systems. Life on Earth is built on carbon. It uses water. It depends on various chemical compounds and minerals. If we want to understand what kinds of life might be possible in other star systems, we need to know what kinds of materials are available there. Comets tell us that water is available in other star systems. They tell us about carbon compounds. They tell us about the chemistry of the broader galaxy. In that sense, every interstellar comet is a piece of information about what might be possible elsewhere in the universe. The discovery of interstellar objects also has implications for the famous Drake equation, a mathematical formula that attempts to estimate the number of intelligent civilizations in the galaxy. The Drake equation multiplies together various factors: the number of stars, the fraction of stars with planets, the fraction of planets suitable for life, and so on. One of the fascinating aspects of the Drake equation is that it shows how the presence of intelligence and civilization in the galaxy depends sensitively on various factors. If intelligent life is rare, the answer comes out to be very small. If intelligent life is common, the answer comes out to be very large. But one implication of the discovery of interstellar objects is this: even if intelligent life is rare, the galaxy is connected. Material can flow between star systems. Information can flow. It is not a collection of isolated islands, but a potentially connected system. That changes the equation in subtle but important ways. To understand 3I Atlas in its fullest detail, we need to appreciate the role of space telescopes in studying this comet. The Hubble Space Telescope, launched into orbit in 1990, has been one of the most productive scientific instruments in human history. On July 21, 2025, Hubble trained its cameras on 3I Atlas. Because Hubble is in orbit above Earth's atmosphere, it is not affected by atmospheric turbulence. It can produce images with much higher resolution than ground-based telescopes can achieve. The Hubble images of 3I Atlas revealed the structure of the coma surrounding the comet with clarity that ground-based observations could not match. The images showed a teardrop-shaped structure of dust surrounding the comet's solid nucleus. This structure was elongated in the direction toward the Sun, showing the influence of solar radiation pressure. The images also showed evidence of jets or outflow features. At the time of the Hubble observation, the comet was still showing the anti-tail structure, the jet pointing toward the Sun. The images helped establish that 3I Atlas was definitely a cometary object with active outgassing and dust production. But for chemical composition, the crucial observations came from the James Webb Space Telescope. The Webb telescope, deployed in January 2022, is an infrared telescope with unprecedented sensitivity and resolution. On August 6, 2025, Webb's near-infrared spectrograph turned its attention to 3I Atlas. The spectrograph does not take pictures the way regular cameras do. Instead, it spreads the light from the comet into a spectrum like a prism, making a rainbow. Different chemicals absorb and emit light at different wavelengths, creating distinctive patterns in the spectrum.